Okay, we're looking at another proof here, and so basically we've got two secants here, and the interesting part of this is what we're trying to prove might be a little perplexing if we just look at that as a concept and think about proofs, and then we can kind of summarize what we did. I think there's an easier way that we can write this right here to make sense of it. So I'm going to go back to, I did give you a hint here to think similar triangles, and I'm going to propose that what we really want to what we might want to really prove is something like this. AP over, so if I want to make cross products, here's what I'm thinking. Think back to similar triangles, and my relationship between corresponding sides in similar triangles is that they are what? Yeah, proportional. So if I want to try to get proportional here, this could be my cross product. So AP and then BP could be right here. Cross products are equal to the cross products here. So I either need AP with CP or AP with DP. And here's where I'm going to need to redraw. I don't know about you, but I need to redraw those two triangles that I'm going to end up with. So right now I don't have triangles. So I'm going to skip the given information. You know that part. And we know that through 2 points, there is exactly one line or one segment, and that's what I'm going to draw in. So chords AD, that's just connecting these 2 points here, and then chord BC. And you could draw those as a dotted line to show that they're extra lines, or however you want to work that. So we have two triangles and they're overlapping here. Let's see if we can work this out. So what I'm going to do is I'm going to actually redraw them and separate them because I need to for myself. So this is the one triangle that I have, is triangle, let's put some letters with that. So I don't have the circle there, but ADP. And then the other one that I'm going to do is the triangle that looks like this, I guess. CBP. And let me highlight that so you can see that. Oh, and I get this nice orange where they overlap. That's beautiful. Okay, so not beautiful pictures, but you can hopefully see, I know my triangles change shapes a little bit, maybe you can do better, but you can hopefully see the two triangles that I have. And I'm going to propose that those are similar to each other. Let's just make sure this will work out in the end. So AP, we said that segment is going to have to be proportional to the corresponding segment in the other one, which looks like CP here. So if I put CP here, AP over CP equals something over BP. Well, BP is here, so it looks like that's going to be my DP. So that matches up with this right here, going down to here, or backwards. If I get to this, then that could lead me to what I'm trying to prove. Okay, so I like my setup. Now the question is, how might I be able to propose? Just trying to focus this a little bit for us. How might I be able to get to those triangles similar to each other? I'm making this assumption here. If the triangles are similar, then I can follow it with this and then this. So easiest way to prove triangles similar, hopefully you're remembering, we have an angle-angle shortcut, and that is by far the easiest way to prove triangles similar. So what do we have going on here that could help us out? Well, I'm seeing an obvious one. Anyone else? Yeah, angle P is a shared angle between the two. Because they were overlapping. So that's going to be an obvious one. In fact, we can go ahead and jot that down. So we use the reflexive property much more with saying segments are congruent in a shared segment, but it certainly works with angles. So that's one. And then the second thing is going to have to be either one of the two angle pairs, either D and B or A and C. So if you think about those angles, I'm first looking at what kind of angles are they in circles. And I'm liking A and C as a choice. Stare at those two angles for a second and tell me what do you know about them. And maybe the first thing that comes to your head is that they're inscribed angles. That's what I'm seeing. An inscribed angle here, vertex on the circle. So angle A would be, if I'm just talking about this angle, angle A would be 1/2 of arc BD. Agree? Okay. And then, so if this is x, that's 1/2 x. Angle C then is an inscribed angle, which is 1/2 of its arc, which is also BD. Do you agree that those two angles are going to be congruent? Okay, even maybe cover up this part of your picture. There we go. Now we've got that nice same intercepted arc corollary to our inscribed angle theorem. So that's going to be my other key here, is getting angle A and angle C congruent, and now I have by angle the two triangles are similar to each other. So angle A is congruent to angle C same intersected arc corollary to your inscribed angle theorem. You can write out more. The inscribed angle theorem we could have used, but then we would have had to use a substitution. Say that it's half the arc and then substitute. So I'm going to go ahead and go with that, and now I'm going to name my triangles. So I've got triangles are similar to each other. Triangle, let's just call this ADP. And then I got to make the other one match, so see what you can do with that. ADP, A is matching up with C, D is matching up with B, and then P. And that's angle similarity shortcut. And I'm basically done. I know I have 2 more steps, but this is exactly what I set up for myself. So I'm just going to throw this in step 6. AP over CP equals DP over BP. Corresponding sides in similar triangles are proportional, and which is part of your definition of similar triangles, and then that follows with AP times BP equals CP times DP, which is obviously what we're trying to prove, and that would be multiplication property of equality, or you could say cross product property of proportions. Either of those is fine. So, how do you feel? That's pretty cool. We used our similar triangles to get to something about circles. I think that's fantastic. But let's kind of make sure that we understand what we actually did here, because this needs to make sense as a concept to us. So if we just kind of try to put this into words, what happened here? What did we actually show is true when we have 2 secant segments intersecting somewhere outside my circle? The length of AP is this entire length here. And then the length of BP is just the outer part. If you take the product of those two, multiply this whole length times this part. I like to say multiply the whole times the outer part. Then you could take the length of CP, which is that whole length, times this part. And those would always be equal to each other. Now, in this case, they almost look equal, but let's look at like a different scenario. We could end up with something, okay, I'm going to freehand the circle. You ready for this? We could end up with something like this, where we have a little bit more extreme, that we have a much smaller one and a much larger one. Same thing here. If I take this entire length and multiply by this, I'm going to get the same thing as if I take this and multiply by that. Weird, isn't it? So I like to abbreviate this one, whole times outer part equals whole times outer part. So if you hear me say that at all, that's where I'm getting it from. Okay, cool. So you're going to try that one with a tangent and a secant. I'm going to give you a hint. Look for similar triangles. This one's a little hard. They're overlapping, sort of like what we just tackled. Good luck. Have fun with it.